Hola, bienvenido a la química. La lectura, well, la lección. Sorry about that. So, lecture 16, part 3, oxidation-reduction, or redox reactions. Now, last time we talked about acids and bases, and those were not so bad. The same is not going to be true of oxidation-reduction. These make baby Jesus cry. You're going to hate them just a little bit. Now, what these are is they are a class of reactions in which you get an explicit exchange of electrons. All of chemistry, well, not all, but a great deal of chemistry involves the movement and transfer and the sharing and exchange of electrons. Redox reactions make that very explicit. So, for example, here you have magnesium giving 2 electrons to chlorine, making the magnesium ion and the chloride ion. And if it were always this simple, you would not come to hate redox reactions. But for this particular reaction, what you're getting is sort of 2 half reactions. Reaction 1 is magnesium metal going to make the magnesium ion and releasing 2 electrons. Meanwhile, chlorine, the nonmetal, takes those 2 electrons to become chloride anions. And yes, we do often split them up this way and refer to them this explicitly. We do have these half reactions, we call them. There are several subcategories of redox reactions. First up, we have combustion. Let's see if I can do this. Fire. Yes, it worked. That's actually pretty good. I'm proud of myself. All right, so fire, combustion reactions. That would be, say, for example, propane plus oxygen yields H2O plus CO2. All right. So that's a combustion reaction. It's hard to see right now, but later you will... well, actually, we could probably definitely cover it right now. The reason it's called oxidation-reduction reactions is because it involves oxidation, which gets its name, once upon a time from adding oxygen. So anytime something reacts with oxygen, binds with oxygen, that's an oxidation. Nowadays, we are a little bit more open and flexible with what we call oxidation. We have a specific definition for it. We'll get to that in just a little bit. But here, your propane, over here on the left, is being oxidized, and the oxygen is being reduced. The other class of reactions are single displacement. You might remember when we talked about precipitation reactions, those are called double displacement. Well, in single displacement, you get something like this. You have a salt plus either a metal or an acid to make a metal plus a salt or a salt and either a metal or a gas. It depends sort of very much on what the reaction is. So, for example, silver nitrate plus copper, that's solid copper plus aqueous silver nitrate, will produce copper nitrate, aqueous, plus silver metal. So it releases the solid silver. And as you can see here, it's actually quite a pretty reaction. It makes a sort of Christmas tree looking thing if you have a coil of copper wire. Next up, we have, for example, zinc plus hydrochloric acid, aqueous, solid, will make us some zinc chloride, aqueous, plus hydrogen gas. Okay. So in both cases, we have our salts, and here we have a metal, and here we have a gas. Okay. So those are just some examples of signal displacement reactions. It's a little bit harder to see, perhaps, but here we have a neutral copper, charge of 0, going to copper 2 plus. So obviously copper is losing electrons, and our silver over here, now silver here, 1 plus, has gained them. So you can already see, again, some of the redox reaction methodology creeping in there. So to learn how to balance redox reactions, yes, it takes a special skill set. You're going to have to learn a new method for balancing a new kind of reaction. I'm sorry about that, but really no way around it. You're going to need to learn some new tools. So first up, we have our oxidation numbers. Oxidation number is not exactly charge, but it's related. So not quite the same thing, but close to it. So first up, we have 4 rules for figuring out the oxidation numbers of the various elements and compounds and so on. The oxidation number of an element is 0. That's for the element in its natural state. Okay, so iron, metal, silver, aluminum, gold, all those would have an oxidation number of 0. But don't forget Brinkelhoff. Okay, so elemental bromine, Br2, also has an oxidation number of 0. Chlorine, oxygen, hydrogen, and so on. Okay, all these have oxidation numbers of 0. They have a neutral charge. They're 0. Okay. Number 2, the oxidation number of a monatomic ion is the charge of the ion. Okay, so whether it's manganese 2 plus, H plus, Cl minus, sodium plus, and so on. Let's say N3 minus, Fe3 plus, whatever. Doesn't matter what the charge is. Any ion, a monatomic ion, this is not true of polyatomic, not polyatomic. Okay. But for any monatomic ion, the oxidation number is just the charge on the ion. 1 plus, 1 minus, 1 plus, 3 minus, and 3 plus. Simple enough. Let's go for some of the more complex and difficult things. So rule 3, non-metals. When they're in compounds, first up we have hydrogen. Hydrogen is either 1 plus with nonmetals or 1 minus with metals. Okay, so HCl, 1 plus. H2O, 1 plus. Aluminum hydride, 1 minus. Sodium hydride, 1 minus. Fairly straightforward. Yeah? Hopefully, yes. Okay. Next up, we have fluorine. Fluorine is super duper simple. Fluorine is always 1 minus, always -1. It's the most electronegative element out there. It never, ever compromises. It's unfriendly, unlikable, kind of toxic. Okay, it's always going to be 1 minus. Never, ever varies. Here we have oxygen. Okay, so let's go ahead and put ox. Usually 2 minus. Okay, oxygen is the second most electronegative element out there. It really, really wants to be 2 minus, and it usually is. Okay? And the exceptions when it's with fluorine, it will take whatever charge is needed. The other exception is peroxide. And in peroxide, each one of those oxygens is -1. Okay. So some examples here, we have H2O, -2. Magnesium oxide, -2. Hydrogen peroxide, it's -1. OF3, oxygen trifluoride, it would be +3. It would be a very unhappy +3, but it's going to be +3 nevertheless. Okay, because fluorine is always -1. And finally for this particular rule, 3C, the halogens. The halogens, in this case, is everything but fluorine. We have chlorine, bromine, and iodine. Okay, those are usually -1. Okay, just like the ions that they would prefer to form. They are very electronegative. They often get their way. The exceptions are when they are paired with oxygen or fluorine. Oxygen and fluorine are very, very electronegative, so they will force the halogens to take other charges, positive charges. So, for example, HCl, chlorine is -1. Hydrogen is +1. ClO3 1-, the chlorate anion, oxygen is -2. Chlorine is +5. We'll be getting into how I work this out later. Let's see. Sodium bromide, bromine is -1. But hypobromite, BrO 1-, it's +1. So maybe some of you are already spotting how we're going to figure this out, but don't worry. I will go into that in excruciating detail. Rule 4. The oxidation numbers of all atoms in a compound are going to add up to the charge of the compound. So in H2O is neutral. We don't write the 0. There's an invisible 0 right there. It's neutral. And hydrogen is +1. Oxygen is -2. Okay. So +1, there's 2 of the hydrogens for a total of +2 and -2. +2 added to -2 equals 0. Similarly, OF3, that's how I figured out what oxygen was, because each fluorine is going to be -1, and there are 3 of them. So that gives us a total of -3. This is a lot like figuring out charges on ions. So that means that oxygen must be +3. And there's only 1 of them, so it's +3. That's how I figured that out. Similarly, ClO3 1-. Each oxygen is -2. There are 3 of them, for a total of -6. Then you have the charge on chlorine, whatever it is, plus the charge on oxygen has to be equal to the total charge on the compound. It has to be equal to -1. Okay, so now you just solve for the charge on, or sorry, not the charge, the oxidation number on chlorine. So chlorine, just add 6 to both sides, and you get +5. So it's not necessarily all that difficult, just, again, kind of tedious. A few more examples. let's see, C2O4 2 minus, that's oxalate. Oxygen is still -2. There are 4 of them, so -8. Now we have 2 carbons. 2 carbons plus the -8 from oxygen is equal to -2, because that's the total charge on the polyatomic ion. So we add 8 to both sides, and we get 2 carbons are equal to +6. So each carbon is +3. So when you look at those together, it's +3 and +3. Then we have -2, -2, -2, -2 from our oxygens. +6, -8. Adds up to the -2 charge on the compound. So those are how we find oxidation numbers. Why do we care about oxidation numbers? Because that's how you determine what is oxidized and what is reduced in a redox reaction. So let's look at permanganate plus just pure silver. It's going to leave you with Mn2 plus and silver 1 plus. As I hope you can see, this reaction is really, really thoroughly not balanced. Now we have to figure out which is oxidized, which is reduced. Oxidation means losing electrons. Oxidation number is going up. Reduction is the other way around. It's gaining electrons. Oxidation number is going down. Now, we already know where oxidation comes from. It comes from the fact that something is reacting with oxygen, once upon a time, at least, historically. And oxygen is very electronegative. Oxygen prefers to go from 0 to 2 minus. It's used to gaining electrons, so it will oxidize things. It will make them lose electrons. It will take electrons away from things. Okay? So that's why oxidation means losing electrons. Reduction that's probably going to be a little bit more annoying, because you're, not gaining electrons, but gaining electrons. Reduction is a gain. That's annoying, yes, but you're gaining the negative charge right there, you see. So your oxidation number is going down. The oxidation number is what's being reduced. That's probably going to annoy a lot of people. So just try and remember this, okay? See if I can draw this out really, really quick. Leo the lion goes grrr. Losing electrons is oxidation. Gaining electrons is reduction. Okay, Leo the lion goes grrr. That might help you remember it. If nothing else, it gave me an excuse to draw badly a lion. There, now he has whiskers. And let's go ahead and give him a majestic chin scruff. All right, so we need to identify which element is oxidized, which element is reduced. I'll go ahead and rewrite our reaction up here. Mn2 plus, silver 1 plus. Now, 3 of the things up here are hopefully going to be very easy to figure out. Okay, silver metal has an oxidation number of 0. Mn2 plus has an oxidation number of 2 plus. And silver 1 plus has an oxidation number of 1 plus. The only even slightly difficult thing here is the manganese that's embedded in the permanganate here in the upper left-hand corner of your screen. Now, oxygen is almost always -2. There are 4 of them, giving us -8. So we have our manganese ion, or our manganese atom, with whatever its oxidation number is, plus the -8 from oxygen equals the charge on the species, and the compound as a whole, -1. We add -8 to both sides, or subtract -8 from both sides, excuse me. The charge, the oxidation number, on manganese is +7. So now we look at the way each metal changes. Silver goes from 0 to +1. The oxidation number is going up. It is being oxidized. Meanwhile, here we have manganese going from +7 on the left, +2 on the right. Okay. The oxidation number is going down, so it is being reduced. So for every oxidation-reduction reaction, that's what you're going to see. You're going to see an element being oxidized and another one being reduced. So you always have to identify the oxidized species and the reduced species. And just to make things even more confusing, you know how we love to confuse you guys. Manganese is the oxidizing agent, and silver is the reducing agent. Because why not throw 2 terms at you that mean the exact same thing, but say it in confusing and exactly the opposite way? Okay. The reason manganese is called the oxidizing agent is because it's causing silver to be oxidized. Agent means a thing that acts or a thing that does something. So the oxidizing agent is the thing that causes oxidation to happen. Likewise, the reducing agent causes reduction to happen. Okay? So the thing that is being oxidized is the reducing agent. Okay? They're the same thing. The thing that is reduced is the oxidizing agent. Being oxidized means you're causing reduction. Being reduced means you're causing oxidation. Okay? Because being reduced means gaining electrons, and being oxidized means you're losing electrons. And the only way you can lose electrons is if something else gains electrons. So you can sort of think of it as parallel to acids and bases. Only instead of gaining or losing an H+, the acidic proton, they're gaining or losing electrons. And just as acids and bases always come in pairs, oxidation and reduction always come as a pair. Never ever separate. So, now that we have identified our oxidized and reduced species, we can start to balance our reaction. Okay, so what we're going to have to do is, step 2, we split, the full reaction into half reactions. Told you they'd be coming back. So, our oxidation half reaction is silver going to silver 1+. Okay. Our reduction half reaction is MnO4 1- goes to Mn2+. Notice how I'm leaving lots of room on both sides of the arrow so that we can keep adding stuff in there. That's going to be super duper important. We're going to need lots of room. So, now that we split it into half reactions, we balance everything but hydrogen and oxygen. Okay? Those are the only 2 we're not going to balance. We balance everything else. So, on the top, we balance silver. 1 silver on the left, 1 silver on the right. Done. Now we go to the reduction half reaction. 1 manganese and 1 manganese. We're done. Okay, that was easy. So now, having balanced everything but hydrogen and oxygen, we're going to go ahead and balance oxygen. So oxygen is what comes next. And you balance oxygen by adding water. So balance O by adding H2O. That's because our redox reactions usually take place in water, and so there's plenty of water available. So up here in our oxidation half reaction, we have silver all by itself, no oxygens, so nothing to balance. Down in the bottom, we have permanganate going to manganese 2+. We have 4 oxygen on the left, so we're going to need 4 water on the right. Let's make that 4 a little cleaner. Okay. So now we've balanced the oxygens. Easy enough. Our next step is balance H by using H+. Simplest thing in the world. So once again, we look at our 2 half reactions, and if there's hydrogen on one side, we balance it out with H+ on the other. So our oxidation half reaction, again, nothing there. Okay? But our reduction half reaction has 8. 4 times 2 makes 8 hydrogens. So we're going to need to add 8 H+ on the left-hand side. And now our hydrogens are balanced. Almost there. We balance charge. Okay. Remember our laws of conservation. Mass, energy, and charge. Okay. We need the charges to be balanced on both sides of our half reactions. And we do that by adding electrons. Now, I want to stress, you're balancing the charges, you're not necessarily bringing them to 0. Sometimes you are bringing them to 0, but not always. Okay. So for our oxidation half reaction, we finally get to do something. We have a silver atom on the right, or on the left, excuse me. It's neutral charge, 0. And we have a silver ion on the right with a charge of +1. We need to make these balance by adding electrons. The only thing electrons can do is bring your charge down. So we balance the charge by adding 1 electron to the right-hand side. So 1 plus and 1 minus adds together to make 0. And now the charge is balanced in the oxidation half reaction. Next thing we need to do is we come down here and we do the exact same thing to our reduction half reaction. We look at the total charges. We have -1 and +8 on the left equals +7. And on the right we have +2 and 0 makes +2. So we need to bring the +7 down to match the +2 on the right-hand side. Adding electrons only reduces charge. Okay, so we add 5 electrons to get a +2 charge. So, not +2, but +5 electrons on the left-hand side. Having balanced the charges, we are now ready to bring our 2 half reactions back together. Unfortunately, I've made rather a mess of this screen, so I'm going to clean it off and rewrite the 2 half reactions. So our oxidation half reaction is silver goes to silver 1 plus 1 electron. Our reduction half reaction is permanganate, NO4 1 minus, plus 8 hydrogens, plus 5 electrons, goes to form Mn2 plus, and 4 water. So the next thing, nearly the last thing, we're almost done balancing this, I promise you, is you balance the 2 half reactions to eliminate, not eliminate, but eliminate the electrons. Okay. Remember, going back to spectator ions, anything that appears on both sides of the arrows is going to cancel out. Okay. So what we're trying to do is we're trying to get our electrons to cancel out and disappear. Redox reactions always involve the exchange of electrons in this way, but we don't want to see them. We want them to disappear, fade into the background, and never do anything. Okay. So what we have to do is we multiply this top reaction by 5, multiply the bottom reaction times 1. When you do that, you get 5 silver goes to 5 silver ions plus 5 electrons. The bottom reaction stays the same. And now, the electron numbers match in our 2 half reactions. And we can add the half reactions together. So, once again, anything that appears on both sides is going to cancel out. In this particular case, the only thing that appears on both sides is the electrons. That's not always the case. Very often you'll have hydrogen and water appearing on either side of the arrows. Okay, they'll be in both reactions. And you'll have to cancel some of those out as well. Unlike the electrons, you might not necessarily lose all of them, though. You'll have some left over usually. So now, let's go ahead and add them together. 5 silver atoms plus 1 permanganate ion plus 8 hydrogen ions. Yes, I know really it should be H3O plus hydronium, but we can pretend. Doesn't really matter all that much. Goes to form 5 silver ions and 1 manganese ion and 4 water. So now we have to check, double check, make sure we did everything right. Okay. Check the atoms and check the charge. Okay. Did we conserve matter and did we conserve charge? That's what we're looking for. So we have 5 silver on the left. We have 5 silver on the right. Yay. I would normally do my bookkeeping thing right now, but I don't want to have to rewrite everything. Okay, we have 1 manganese on the left. We have 1 manganese on the right. We have 4 oxygen on the left. We have 4 times 1 is 4 oxygen on the right. We have 8 hydrogen on the left. And 4 times 2 is 8 hydrogen on the right. Okay, so conservation of matter, check. Next up, we're going to balance our charges. Or we're going to check that our charges are balanced, I should say. Okay, we have 0, -1, and +8. Add those all together, you get +7 on the left. Here we have 5 times 1 equals +5, and +2, and 0. Add those all together, you get +7 on the right. So charges balance! Huzzah! Okay, so that means we're good to go. This is the balanced redox reaction. And that's why you can't just look at a redox reaction and know right away. You have to, how it's going to be balanced. Okay. You have to figure out how they're changing their oxidation numbers, and then you're going to have to throw in random amounts of acid and water to get it to actually balance out. So it's a fairly complicated process. It's what I've shown you is 8 steps, okay? But there is a possible 9th step. So we go ahead and throw that in there. Step 9, if in base, add OH minus. Okay. Those first 8 steps, everything we did was we assumed it was taking place in acid. If it takes place in an acid solution, you're going to have lots of hydronium floating around, a lot of H+. That's just fine. But now we are adding the possibility that it could be taking place in a basic solution. That's always possible, and it's easy enough to deal with. So let's look at our reaction. I'll write it out again. So we need to get rid of our H plus right there. Okay, you're not going to have an excess of hydronium in a basic solution. You will have an excess of hydroxide. So what you do is you add OH minus to both sides. And what happens here on the left, okay, where the H plus is, 8H plus 8OH minus is 8H2O. Then anything that appears on both sides is going to cancel out. It's not necessarily going to cancel out entirely, but it should cancel out somewhat. So we have 4H2O on the right. Those are going to disappear entirely. And on the left, 8 becomes 4, because 8 minus 4 is 4. Okay. So what that means is that if this takes place in a basic solution, it's 5 silver plus permanganate plus 4H2O yields 5 silver 1 plus manganese 2 plus 8 hydroxide. So we have two possible answers here. The first is the one that takes place in acid, and here's the one where it takes place in base. So just go ahead and pay attention to what you're being asked to solve specifically. Is it in an acid solution or is it in a basic solution? Now what I'm going to do now is I'm going to go ahead and show you, I'm going to write out the 8 steps, or the 9 steps, 8 and 9. And that'll be it for this video. But then in the next video, it would just be me working through a couple more examples for you. So first, find the oxidation numbers for all the species. Second, split into half reactions. Third, balance everything but hydrogen and oxygen. Fourth, balance oxygen by adding water. Go ahead and make this clear. That's a comma. This is a 2. Well, that's H2O. This is a comma 2. Okay. Fifth, we balance hydrogen by adding H plus. Sixth, balance charge by adding electrons. 7, balance the half reactions against each other so that the electrons disappear. This means multiplying. And 8, add half reactions together. And 9, if in base, we add hydroxide. Let's go ahead and add a 10th step just to make it nice and round. We double check, okay. We double check that the elements all balance, that charge is all balanced. Now let's go ahead and throw in the third, that coefficients are reduced. Okay. So remember, for balancing a regular reaction, you want the lowest possible coefficients. You want the lowest possible coefficients here as well. And it's possible when you balance the two half reactions together up against each other in step 7, you might end up with a common denominator or something. So just go ahead and double check that as well. So those are your 10 steps, and that'll be it for this video. See you next time.